Hi everyone, today we are going to be discussing Lab 6. The purpose of this lab is to study the magnetic interactions and currents as a falling bar magnet interacts with an aluminum tube and how it relates to Faraday's law. We will also compare our observations with the computational model that we make. To do this, we're going to be using Biot-Savart law, which describes a magnetic field made by a constant electric current, and Faraday's law, which describes how magnetic flux produces electromotive force on a function of magnetic field changes over time. We will also be considering Newton's second and third law, which says force equals mass times acceleration, and for every force there's an equal and opposite reaction. The mass of our magnet was 0.025 kilograms, and the mu was 3.804 amps times meters squared, which we found last lab. And these are the measurements for our tube, and we ran 5 different trials, and our average time was 2.856 seconds. In the computational model, the first thing I did was establish the initial conditions, constants, and measurements of the tube and magnet that we made on the previous slide. The next thing that I did was use Biot-Savart law to find the magnetic field on the bar magnet, and then I used that to find the magnetic flux as it is a function of magnetic field over time. And then I found the forces, which included gravitational force on the magnet, magnetic force on the magnet from the tube, and net force. Although it's difficult to see on how small the graph is, on the velocity versus time graph, we see that there's a rapid increase in velocity, which will suddenly plateau until the end where the magnitude of velocity increases again. So comparing our observations in the computational model, we see that our experimental time was 2.856 seconds, whereas our computational time was 11.215 seconds. So we might ask why these numbers differ, and first off, we considered air resistance as negligible, and we only considered gravitational force and the force on the magnet from the tube. We also assumed that the bar magnet constantly acted as a magnetic dipole, in which we applied the Biot-Savart law to. It's also important that we consider sources of error. So the first one is error in starting and ending the stopwatch. Another one is surrounding interference of electronics and magnetic forces from lab equipment and devices. And we also did not consider friction. For our discussion, our first question was, what if the resistivity of the conductor were reduced to as close as possible to 0? And how would the dynamics of the falling magnet change? To this, I answered that the induced current of the aluminum tube would increase in magnitude accordingly, which would cause the magnitude of the magnetic force on the magnet to increase. This would cause the falling magnet to fall slower or not at all if the magnetic force counteracts gravitational force entirely. Our second discussion question is, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The currents would not be continuous, so the induced current would decrease in magnitude. There would also be less magnetic force on the magnet, so the magnet will fall much faster.